Hi students, in our previous video classes, we discussed about the liquid drop model and the shell model. In today's session, we are going to discuss collective model and Meson theory of nuclear forces. Now, collective model proposed by H. Bohr and Ben Mortensen combines the features of both the liquid drop model and the shell model. Now, you know that the liquid drop and shell model were able to account for most of the nuclear behavior or for many features related to the nuclear forces. Now, the collective model combined the features of both these models, and this model also takes into account factors such as the non-spherical shape of nuclei except in even nuclei, and also the centrifugal distortion experienced by a rotating nucleus. So, in addition to the features taken into account by the liquid drop and shell model, the collective model also took into account the factors such as the non-spherical shape of nuclei and the centrifugal distortion experienced by rotating nuclei. Now, the detailed theory is able to account for the spacing of excited nuclear levels. Next, we go on to the discussion of Meson theory of nuclear forces. As you all know, how that a molecule is held together by the exchange of electrons between the adjacent atoms. Similarly, a theory was proposed so that the nucleons in the nucleus are held together by exchanging some kind of particles between them. That is, the nuclear forces that hold the nucleons together in the nucleus is such that the nucleons are held together by the exchange of some kind of particles. അതായത് ഒരു മോളിക്യൂൾ ഉണ്ടാവുമ്പോൾ അതിലത്തെ കോൺസ്റ്റിറ്റ്യുവൻ്റ് ആയിട്ടുള്ള ആറ്റംസ് ഇലക്ട്രോൺസ് എക്സ്ചേഞ്ച് ചെയ്തുകൊണ്ട് ഒരുമിച്ച് നിൽക്കുന്നത് പോലെ ഒരു ന്യൂക്ലിയസിലെ ന്യൂക്ലിയോൺസ് എന്തോ ഒരു തരം പാർട്ടിക്കിൾസ് അന്യോന്യം കൈമാറിക്കൊണ്ടാണ് ഒരുമിച്ച് നിൽക്കുന്നതെന്ന്. അതായത് ഈ ന്യൂക്ലിയോൺസിനെ ഒരുമിച്ച് നിർത്തുന്ന ന്യൂക്ലിയർ ഫോഴ്സിന് കാരണം ഈ എക്സ്ചേഞ്ച് ഓഫ് പാർട്ടിക്കിൾസ് ആകാം എന്നൊരു തിയറി മുന്നോട്ട് വയ്ക്കപ്പെട്ടു. So, it is possible that the nucleons in the nucleus are held together by the exchange of some kind of particles between them. In 1932, Heisenberg suggested that the nucleons in the nucleus are held together by the exchange of electrons and positrons. But exchange of electrons and positrons means the neutron gives out an electron, and that electron is received by a proton. Now, the neutron that gave out the electron becomes a proton, and the proton that received the electron should become a neutron. Similarly, a proton should give out a positron and become a neutron, and the neutron that receives that positron should become a proton. In this manner, by the exchange of electrons and positrons, the nucleons are held together in the nucleus. അതായത് ഹേസൻബർഗ് സജസ്റ്റ് ചെയ്തത് എന്താ വെച്ചാൽ ന്യൂക്ലിയസിനുള്ളിലെ ന്യൂക്ലിയോൺസ് ഒരുമിച്ച് നിൽക്കുന്നത് ഇലക്ട്രോൺസും പോസിട്രോൺസും തമ്മിൽ എക്സ്ചേഞ്ച് ചെയ്തുകൊണ്ടാണ് എന്ന്. അതായത് ന്യൂട്രോൺ ഒരു ഇലക്ട്രോണിനെ പുറത്തുവിട്ട് ആ ഇലക്ട്രോണിനെ അടുത്തുള്ള ഒരു പ്രോട്ടോൺ അക്സെപ്റ്റ് ചെയ്യുന്നു. അതായത് ന്യൂട്രോൺ ഇലക്ട്രോണിനെ പുറത്തുവിടുമ്പോൾ അതൊരു പ്രോട്ടോണായി മാറുകയും ഈ ഇലക്ട്രോണിനെ സ്വീകരിക്കുന്ന പ്രോട്ടോൺ ഒരു ന്യൂട്രോൺ ആയി മാറുകയും ചെയ്യും. അതുപോലെ ഒരു പ്രോട്ടോൺ ഒരു പോസിട്രോണിനെ പുറത്തുവിടുന്നു, അങ്ങനെ അതൊരു ന്യൂട്രോൺ ആയി മാറുകയും ആ പോസിട്രോണിനെ റിസീവ് ചെയ്യുന്ന ഒരു ന്യൂട്രോൺ ഒരു പ്രോട്ടോൺ ആയി മാറുകയും ചെയ്യും. Iteratil, in this manner, the nucleons in the nucleus are held together by the exchange of electrons and positrons. This theory was put forward or suggested by Heisenberg in 1932. Now, emission of electrons or positrons all come under beta decay, and calculations based on beta decay showed that the forces resulting from this, if such an exchange is taking place, and if we are calculating the forces resulting from this exchange, the that force is very much smaller, say by a factor of 10 raised to 14 times smaller when compared to the actual nuclear forces. Okay, so exchange of electrons and positrons are a part of beta decay, or emission of electrons and protons are a part of beta decay, and calculations based on beta decay showed that if the exchange of electrons and positrons are responsible for nuclear forces, and if that forces are calculated based on beta decay, then it was found that the value of the force is very much smaller, about 10 raised to 14 times smaller than the actual nuclear force. Thus, in 1935, Hideki Yukawa put forward the proposal that particles having intermediate mass between electrons and nucleons are responsible for the nuclear forces. He did not say what are those particles, but he told that there might be some other particles, not electrons or positrons, but some other particles having mass between that of the electrons and nucleons, which are responsible for the nuclear forces. It is the exchange of these particles between the nucleons which is responsible for the nuclear forces. Today, these particles have been found out to be pions, what are called pions. Okay, so when Yukawa proposed this theory, these particles were not discovered. He just put forward that there might be some particles having mass between that of electrons and nucleons, which when exchanged from between the nucleons are responsible for the nuclear forces. But today we know that those particles are called pions, and pions are of three types: pi plus, pi minus, and pi zero, which are, and they are the members of an elementary particles called a class of elementary particles called mesons. Okay, so pions are also called pi mesons. Now, what are the features of Yukawa's theory? Okay, according to Yukawa's theory, every nucleus must continuously emit and absorb pions. He did not know that those particles were pions, but now we say that uh, because we know that those particles are pions, we place it in that theory too. So every nucleon must continuously emit and absorb pions. That is the first feature. Then, uh, if another nucleon is nearby, an emitted pion may shift across it to the other nucleon, then returning to the parent nucleon. The associated change in momentum is equal to the action of the force. So, the second feature of this theory was that if a nucleon emits a pion, and either that nucleon itself can absorb that pion, or if there is some other nucleon nearby, then this pion will shift and it will be absorbed by the neighboring nucleon instead of returning to the parent nucleon. Now, when the pion shifts from one nucleon to another, there will be a change in momentum which is equivalent to the action of the nuclear force. And Yukawa's theory could also account for the fact that nuclear forces are repulsive at very short ranges and attractive at greater nucleon distance. So this is a very important property of nuclear force. That is, nuclear force or the forces inside the nucleus is repulsive at very short range and attractive at larger distances. Now, Yukawa's theory that these particles are continuously exchanged between the nucleons could account for the fact that nuclear forces are repulsive at very short range and attractive at greater nucleon distances. How could Yukawa's theory explain for this fact? So this is what Yukawa told. See, there is a neutron here. Now it is giving out a pi plus particle. It will travel with the velocity of light, and there is a neighboring neutron here, and when this pi plus is absorbed by this neutron, it becomes a proton. Okay, and similarly, they keep on exchanging particles, and they remain in the nucleons are held together. Now, we were discussing how the nuclear forces are repulsive at short distances and attractive at larger distances. It was explained by imagining two boys exchanging balls. Now, if they are very close to each other, then and they throw the ball, then um, it is just like they are snatching the balls from each other's hand. So, if the boys are standing very close to each other and one boy throws the ball, then the other boy has to move back to catch the ball. That is if the that is the force becomes repulsive. That is, if the particles come closer than a particular limit, the force between them becomes repulsive. They are going back. That is, the first case is when the two nucleons are very close to each other, then the force between them becomes repulsive. That is, if the two boys are very close to each other and they throw the ball, then one of them throws the ball, then the second boy has to move back to catch the ball, something similar to repulsion. On the other hand, if the particles are a bit far away from each other, that is, the two boys are a bit far away from each other, and one of them throws the ball, then the other boy has to come forward to catch the ball. That means the force between them is something similar to attraction. That is, the boys have to come nearer to catch the ball. That is, if the nucleons are far away, then or at larger nucleon distance, the force between them is attractive. Whereas if the particles are or the nucleons are close to each other, then the force between them is repulsive. Okay, so in this manner, Yukawa's theory could explain the nuclear features of the nuclear forces. So the 3 points in Yukawa's theory were: every nucleon continuously emits and absorbs some kind of particles having mass between that of electron and nucleons. That is, today we know that those particles are pions. Now, if another nucleon is nearby, the emitted pion may shift across it to that nucleon instead of returning to the parent nucleon, and the associated change in momentum is equivalent to the action of the force. Now, Yukawa's theory could also account for the fact that nuclear forces are attractive at very short range. Are repulsive at very short range and attractive at greater nucleon distance. Now, one problem in this theory was that if the nucleons are continuously emitted and absorbed, if the nucleons continuously emit and absorb ions, then why are neutrons and protons not found with masses other than their usual masses? That is, when a neutron gives out a pion and gets, a neutron is giving out a pion, and it becomes a proton. That means, and another proton is absorbing, or another neutron is taking up that pion. That means there must be an intermediate mass of neutron plus pion which is not equal to that of the proton. So when you examine the nucleons, you must be able to see masses other than that of the neutrons and protons. That is, neutron plus pion, proton plus some kind of pion. Such mass particles with difference in mass, or these nucleons with masses other than the expected mass of the proton and neutron should have been present if the nucleons are continuously emitting and absorbing pions. അതായത് ഒരു ന്യൂട്രോൺ ഒരു പയോണിനെ പുറത്ത് വിട്ട് മറ്റൊരു ന്യൂക്ലിയോൺ ആ പയോണിനെ സ്വീകരിക്കുമ്പോൾ അതിന്റെ മാസ് കൂടണം. ഈ പുറത്ത് വിട്ട ആളുടെ മാസ് കുറയും വേണം. അതായത് നമുക്ക് നമ്മൾ ന്യൂക്ലിയോൺസിന്റെ മാസുകൾ എക്സാമിൻ ചെയ്യുമ്പോൾ ന്യൂട്രോൺ ആൻഡ് പ്രോട്ടോൺ മാസുകളോട് കൂടിയ ന്യൂക്ലിയോൺസിനെ മാത്രമേ, അതായത് ന്യൂട്രോണിന്റെയും പ്രോട്ടോണിന്റെയും മാസുകൾ മാത്രമേ നമുക്ക് ഈ ന്യൂക്ലിയോൺസിൽ ഡിറ്റക്ട് ചെയ്യാൻ പറ്റുന്നുള്ളൂ. അല്ലാതെ ഒരു ന്യൂട്രോൺ പ്ലസ് പയോൺ അല്ലെങ്കിൽ ന്യൂട്രോൺ മൈനസ് പയോൺ, പ്രോട്ടോൺ പ്ലസ് സം കൈൻഡ് ഓഫ് പയോൺ, പ്രോട്ടോൺ മൈനസ് പയോൺ മാസ്, അങ്ങനത്തെ ഇന്റർമീഡിയറ്റ് മാസോട് കൂടിയ ന്യൂക്ലിയോൺസിനെ നമുക്ക് കാണാൻ സാധിക്കുന്നില്ല. അപ്പോൾ വാട്ട് ഈസ് ദ മിസ്റ്റേക്ക് ദർ ഓർ വാട്ട് ഹാസ് ഹാപ്പൻ ദർ? Now here the uncertainty principle, to explain this, ഇത് explain ചെയ്യാൻ uncertainty principle comes to our help. That is, uncertainty principle limits the accuracy with which certain combinations of measurements are made. We know that. What is the function? What does uncertainty principle do? It limits the accuracy with which certain combinations of measurements are made. That is, position, momentum measurements. It brings in an inaccuracy. If one is measured accurately, the other won't. We won't be able to measure the other one accurately. Similarly, another combination is energy and time, and that is what we make use here. That is, according to the uncertainty principle, delta E delta T must be greater than or equal to h cross by 2. That is, a nucleon can exchange pions without a change in mass, or without if a change in mass take place, there will be a change in energy. Delta E is equal to delta mc square. So that is without violating the law of conservation of energy. The nucleons can exchange pions provided that such absorptions and emissions take place very, very fast, so that it is impossible to determine whether a change in mass or a change in energy is involved or not. അതായത് ഈ നമ്മൾ പറഞ്ഞത് എന്താ വെച്ചാൽ, നമ്മുടെ ന്യൂക്ലിയോൺസിനെ കൺസിഡർ ചെയ്യുമ്പോൾ നമുക്ക് ഒരിക്കലും ന്യൂട്രോണിന്റെയും പ്രോട്ടോണിന്റെയും മാസ് അല്ലാതെ ന്യൂട്രോൺ പ്ലസ് ദ മാസ് ഓഫ് എ പയോൺ, അല്ലെങ്കിൽ പ്രോട്ടോൺ പ്ലസ് ദ മാസ് ഓഫ് എ പയോൺ, അല്ലെങ്കിൽ ന്യൂട്രോൺ മൈനസ് മാസ് ഓഫ് എ പയോൺ, പ്രോട്ടോൺ മൈനസ് മാസ് ഓഫ് എ പയോൺ എന്നുള്ള ന്യൂക്ലിയോണുകളെ, ഈ മാസുകളോട് കൂടിയ ന്യൂക്ലിയോൺസിനെ നമുക്ക് കാണാൻ സാധിക്കുന്നില്ല. അതായത് പക്ഷെ ഇവര് ഈ എക്സ്ചേഞ്ച് നടത്തുന്നുണ്ട് താനും. അപ്പോ how can you account for that absence of intermediate mass or intermediate energies? There we make use of uncertainty principle. According to uncertainty principle, delta E delta T greater than or equal to h cross. That is, if delta T is very, very, very small, that is, the exchange of the particles take place in a very short duration of time, then what will happen? The change in mass or change in energy can take place without violating the law of conservation of energy. That is, this violation will not take place if the absorption or emission takes place so fast that you are not able to measure the change in mass or change in energy. So, an event in which delta is conserved is not prohibited as long as the duration of the event do not exceed h cross by 2 delta. So here actually we feel that the energy is not conserved. So an event in which delta E is not conserved, it is not delta E is conserved, and in event in which delta E is not conserved is not prohibited. I made a very big mistake here in what I've written. So, an event in which delta E is not conserved is not prohibited. അതായത് ഡെൽറ്റ ഇ കൺസേർവ്ഡ് ആവാത്ത ലോ ഓഫ് കൺസർവേഷൻ ഓഫ് എനർജി കൺസേർവ്ഡ് ആവാത്ത ഒരു ഇവന്റ് പ്രൊഹിബിറ്റഡ് അല്ല, നടക്കാൻ സാധിക്കാതെ ഇരിക്കില്ല. എപ്പോ അത് നടക്കാനെടുക്കുന്ന സമയം എച്ച് ക്രോസ് ബൈ ടു ഡെൽറ്റ. ഫ്രം വേർ ഡിഡ് യു ഗെറ്റ് ഇറ്റ്? യു ഗോട്ട് ഇറ്റ് ഫ്രം ദി അൺസർട്ടിനിറ്റി പ്രിൻസിപ്പിൾ. അതെടുക്കാൻ ചെയ്യാൻ എടുക്കുന്ന സമയം, ആ ഇവന്റ് നടക്കുന്ന സമയം എച്ച് ക്രോസ് ബൈ ടു ഡെൽറ്റ, ടു ഇൻറ്റു ഡെൽറ്റ ടിനേക്കാൾ ചെറുതാണെങ്കിൽ നമുക്ക് കൺസർവേഷൻ ഓഫ് എനർജി പാലിക്കപ്പെട്ടിട്ടില്ല എന്ന് തോന്നിയാൽ പോലും അത്തരം ഇവന്റുകൾ നടക്കും. Okay, so an event in which delta is not conserved, please take care here, it is not conserved, is not prohibited as long as the duration of the event do not exceed h cross by 2 delta. Okay, now next what we are going to do is we are going to uh, determine what is the mass of the particle that Yukawa predicted. Today we know that it is pion, but Yukawa did not know that that particle was pion. He just predicted that it might be some particle with mass between that of an electron and the nucleon. Let us see what is the mass of this particle pion and does it match his prediction. So let a pion travel between two nucleons. Now a pion is traveling between two nucleons with a velocity nearly equal to c. The two nucleons are separated by a distance r. Here the proton is giving a pi plus and the proton becomes a neutron, and the neutron accepting the pi plus becomes a proton. Now, because of this emission, there is a temporary energy discrepancy of m pi into c square. There will be a decrease in energy of m pi c square here, and there will be an increase in energy of m pi c square here because it is receiving the pion and this is losing the pion. Okay, let t be the time taken for traveling this distance, so that t is equal to r by v equal to r by c, distance by velocity. Now, substituting in our equation, delta E, delta T nearly equal to H cross. You need not take it as H cross by 2, you can leave it as H cross. So, delta is m pi c square into r by c is nearly equal to H cross. M pi is nearly equal to H cross by rc, and I substitute the values. H is 6.6 into 10 raised to minus 34. H cross, that is H divided by 2 pi, is 1.05 into 10 raised to minus 34 joule second divided by the radius of the nucleus, 1.7 into 10 raised to minus 15 into velocity of light, 3 into 10 raised to 8. You get it nearly equal to 2 into 10 raised to minus 28 kilogram. And this was predicted to be the mass of the pion, which is about 220 times the rest mass of an electron. So it is more massive than an electron, but less massive than the nucleons. Now, about the discovery of the pion, Yukawa predicted the presence of a particle like pion, but when was it actually discovered? It was 12 years after Yukawa's proposal that pions were discovered. Okay, Yukawa put forward the theory of nuclear forces, his exchange theory, but it was after 12 years that the pions were discovered. Okay, two factors contributed to this belated discovery. That is, the discovery of pions became late because of two factors. That is, at least m pi c square of energy, that is about 140 million electron volt of energy, must be supplied to a nucleon to emit a pion. Such high energy particles are found in nature only in cosmic radiations. So, to obtain in nature, it is found only in cosmic radiations, but to do these experiments in our laboratory, what we needed beam of particles having energy which is this much high, that is about 140 million electron volts high. So this was made possible. Such high energy beam of particles could be produced only after the discovery of accelerators, which we have already learned. Okay, so it was after the discovery of accelerators that these studies became more effective and easier, and pions were discovered. The second reason for the lag in the discovery of pions was that the pions are highly unstable, or it has a very small lifetime. The charged pions like pi plus and pi minus have a very short lifetime of 2.6 into 10 raised to minus 8 second, which makes their detection very difficult. And the lifetime of a neutral pion is 8.7 into 10 raised to minus 17, still smaller seconds. So all these made the discovery of the pion lag between its prediction. One was experiments could be done on the nucleons and related to the emission or absorption of pions only after the discovery of high energy accelerators. And another reason which made the which caused the lag between the prediction and experimental discovery of pion is that it's highly unstable. It has a very short mean lifetime. Okay, so I think the Yukawa's theory of um, nuclear forces, that is the Meson theory of nuclear forces, and the discovery of pions is clear to all of you. In this session, we discussed firstly the collective model, then we discussed about how the exchange of particles will be responsible for holding the nucleons together and hence be responsible for the nuclear force. Heisenberg suggested that this exchange could be due to the exchange of electrons, but Yukawa put forward that it might be due to the presence of exchange of emission and absorption of particles, like having mass between that of electrons and nucleons. Later, it was discovered that such particles are um, pions. Then we discussed how, even though we feel that in this process the law of conservation of energy is violated, how is such an event allowed by taking the help from the uncertainty principle. And then we calculated the mass of the pion, and we discussed in detail how the discovery of the pion um, lagged behind its experimental prediction. So I hope this session is clear to all of you. If you have any doubt, please do contact. Thank you.